Hello and good afternoon. The Public Outreach and Education Committee of the Astronomical Society of India welcomes you to the discussion series Ask an Astronomer. I am Sarita Veg, and joining me are Professor Aniket Sule and Professor Harvinder Kaur from the ASI POEC. Also helping out with the organization is Atharva Pathak. Our eminent astronomer for today is Professor Somak Raychaudhury from IUCAA Pune, and our theme for discussion is black holes. Professor Somak will be giving a short presentation about black holes, which will be followed by a discussion. I invite our participants and viewers to jot down their questions in the chat box, and we will be taking them up. I would first like to introduce our guest astronomer and speaker. Professor Somak Chaudhary is the director of the Inter-University Center for Astronomy and Astrophysics, IUCAA, which is in Pune. He graduated from Presidency College, University of Calcutta, with further studies at the University of Oxford, UK. After his PhD from the University of Cambridge in UK, he worked at the Harvard Smithsonian Center for Astrophysics, USA. After teaching for over a decade at the University of Birmingham in UK, he returned to India as head of physics and dean of sciences at Presidency University, Kolkata, before he became the director of IUCAA. His research involves a wide range of topics in cosmology and astrophysics from the ground and from space. May I now request Professor Somak to begin his presentation?
Thank you very much. Thanks, Sarita. And thank you, everybody, and thanks to the ASI Public Outreach and Education Committee for giving me this opportunity to interact with people who are interested in astronomy. I'm going to talk about black holes today, so let me share my my slides. I've got a few slides to begin with, and then let's see how the discussion goes. So I talked about, I called this presentation How to Weigh Black Holes, because we'll focus on not just how black holes can be detected, but how their masses and characteristics are found. But let's just go to the very basics and look at what I mean by black holes. And so I want to start from what everybody knows from school, and that is to do with a view of gravity that is taught to us in high school. So this is Newton's way of looking at gravity. And I start by saying that even though black holes are very much to characterize black holes, you really need a new way of looking at gravity. You can have the basic idea from Newton, and Newton talked about how gravity is a force between two objects. We are taught this in school, that two masses pulling each other leads to an acceleration that's proportional to the masses that are pulling the object, but also inversely proportional to the square of the distance between them. And so that leads to this concept of an escape velocity, which essentially is this very simple formula that tells you that if you're trying to escape from the gravity of an object that you are attached to, or you're standing on, like the Earth, then you need something that is this quantity, 2gm/r square root, that kind of velocity to escape the gravitational field of the object. This gives us an idea, and so the idea is so let's look at what this amounts to. This is quite a large amount. For example, for the Earth, you need 11 kilometers per second, or about 43,000 kilometers per hour. So this is not something like the speed of a car that can you can drive so that you can go away from the Earth. Right? From the sun, that amounts to 600 kilometers a second. The Earth is moving around the sun at a speed of 30 kilometers a second. So this is why the Earth is not escaping from the sun. So this itself sets, from Einstein's way of looking at gravity, this kind of sets the scale of what escape velocities are. So right from a few years after Newton, people started asking, so what happens if there is an object that has enough mass, and you need a big mass and a small radius for the m/r connection to be a combination to be very high. It is very high, such that it's higher than the speed of light. So even light cannot escape from such an object. At that time, people didn't know that nothing can travel faster than the speed of light. This we knew only in the 20th century from Einstein. But but it was clear that light travels at a very high speed, and so if light cannot escape from this object, we now know nothing can escape. But there, people were more concerned with what this will lead to, and this will lead to something called a dark star. So you can see how you can do this. You can take, because it's a combination of mass over radius. You can keep mass constant, but squeeze it to a very small size so that the m over r combination becomes very large, and so the escape velocity becomes very large, right? And if can you make it as high as the speed of light is a question. Even in the Newtonian sense, you can think about this. So let's see what it would take to how small does an object need to be to turn into a black hole, or how big or how small is a black hole. If you look at the relative sizes of things in the solar system, the sun is not yet, something that can turn into a black hole. It's a small star. We'll come to that a little later, but you can already see there's a huge difference in sizes even within the solar system. These are the relative sizes of things. Now, do you want to squeeze the sun in order to make it a black hole and make it the size of Jupiter or the Earth, or even smaller, maybe an asteroid, to make it into a black hole? Is that what it is? It turns out that there is this formula that came out of the early work on general relativity. You need relativity to general relativity, not Newton's formulation, to figure out how small this needs to be in order for it, because gravity, the Newtonian gravity calculation doesn't really work if you make things very dense and things, you're talking of velocities that are very close to the speed of light. And so you need a proper formulation, but the formula that comes out of it is very easy. It's 2gm over c squared. It's called the Schwarzschild radius. And if you plug in these numbers, like for example, the sun's mass into a formula like this, you get that in order for the sun to become a black hole, it needs to be less than 3 kilometers in size. For the Earth to become a black hole, you often read in the papers when such and such experiment will start, the Earth might turn into a black hole. I mean, the Earth actually needs to go and become smaller than a centimeter in radius before it from that formula. So it is possible to squeeze everything, including you, into a black hole in principle, in theory, because it tells you that if you have mass, then if you can be squeezed into a sphere of that radius, you become a black hole, right? So in principle, everything can become. In practice, we will see whether you can become a black hole or not. Can the sun become a black hole? Can the Earth become a black hole? So in order to do this, you have to really use Einstein's idea of gravity, which is a modification of it. Newton was not wrong, but Newton's theory of gravity is incomplete. It cannot deal with velocities that are very high and close to the speed of light, or densities of masses that are extremely high. And so Einstein generalized Newton's concept, but actually in order to do that, changed it completely, the way of looking at gravity. In Einstein's formulation, gravity is not a force. It is a way in which a mass has a geometrical effect on space-time. That is not a force. What happens is that if you have a massive object, it distorts space locally, and things move along space, along that distorted space, and thus they can have curved paths. And so even light can move along a curved path, because if it goes around a massive object, because it's going along a curved space-time. So the idea in a kind of cartoon sense, you see this picture quite a lot. The idea is that, say, the sun distorts, curves space-time around it. This is not really, I mean, it's showing this in 2 dimensions, but so it's not really true, but it gives you the idea that, and you can see the Earth going around the sun. Earth also has mass, so it kind of distorts space-time a little, but because the Earth is going around the sun, not because there's an invisible string of gravity pulling it to the sun, but it's because space-time itself is curved, and the Earth is trapped in the curved space-time, and it's moving in the normal natural trajectory that it can follow in that curved space-time. And I've already told you that it cannot escape from the sun because it needs a very high escape velocity. So the idea is that that locally something is trapped in the gravity of an object because the curved space-time is curved. And so you can think of a black hole as something in which the size is so small and the density so high that locally the space-time is curved so much that nothing can come out of this well, and not even light. And so that becomes a black hole. So it's worth thinking about it in those terms. And once you start thinking about it in those terms, you can work out mathematically a lot of these things. And this is what Schwarzschild did, for example, very soon after Einstein's theory, and found what is known as an event horizon, which means that this is the minimum radius and to which you can get information out of near a black hole. Beyond the event horizon, which means inside the event horizon, you can't have any information coming out of there. Right? That's why it's called a black hole. We have a lot of myths about black holes. Black holes don't go around sucking things in from everywhere. They are not vacuum cleaners. They, for example, if the sun became a black hole, the planets are not going to fall in. It's going to be a very cold place, of course, because there will be no light. But the Earth will go around the sun as it normally does because it feels the gravity of the sun. The effect of a black hole doesn't stretch beyond very, very large distances. So the sun's, if the sun does turn into a black hole, it won't. It will never become a black hole. But if it does, then you read in science fiction that all the planets falling into the star, etc. In practice, black holes, the range of black holes in kind of pulling things in is not very, very large. And so black holes are not dangerous in that way, that they're not coming to get you, but don't go very, 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 very near a black hole because you're going to fall in. So how many times? There are many, many different kinds of black holes that there are. There are these black holes that are very close to the mass of the sun. These are called stellar mass black holes. And typically, till a few years ago, we knew about such black holes, which are about 5, 10 times the mass of the sun. But now, as I'll say a few minutes later, we've gone, that mass has gone up to about 140 times. So we now know 3 black holes that are more than 100 times the mass of the sun. So these are stellar mass black holes, but now it's getting very, very high and going into this range of what is known as intermediate mass or mid-mass black holes. But then there are supermassive black holes that sit in the middle of galaxies. There's one per galaxy, and this goes from about 1 million times 10 to the power 6 to 1 billion times, a few billion times the mass of the sun. So these are huge, and there's always been this idea of, can stellar mass black holes turn into supermassive black holes by merging together? Otherwise, how would supermassive black holes come? There are no stars that massive that can turn into black holes. And people have been saying for a long time, if really stellar mass black holes turn into supermassive black holes, then there should be intermediate products. And we don't see, for example, 10 to the 3, 10 to the 4, 10 to the 5 times the mass of the sun black holes. But now we've started finding things that are in the hundreds. And so things are getting a little interesting. So let's talk about, for example, the supermassive black hole first. As you know, this year's Nobel Prize, last year's Nobel Prize went to the characterization of the black hole in the middle of our galaxy. Our galaxy looks like this. We live in a planet, on a planet near the sun, which is in the disk of the galaxy, which is very flat. About 75% of all galaxies look like this. They have transient spiral structures and they're rotating fast. They have a disk galaxy. And right in the middle here, right in the middle, I hope you can see my cursor, is a black hole, a supermassive black hole. And we knew about it for a long time, but the people who actually weighed that black hole, found its mass and found its various characteristics, got the Nobel Prize this year. And you can see that there are quite a lot of difficulties in doing this. And they got the Nobel Prize not just for discovering the black hole, but actually using the technology that enabled this, which is amazing. So first of all, you can see in the plane of the galaxy, there's a lot of dust. And to look towards from here towards the center of the galaxy, you really need to look through that dust. And then you really, the way they did it was they looked at the dynamics of stars that are very close to that black hole. In order to do that, you had to detect these stars very close. It's for example, if you look at the solar system from the orbits of the planets, you can find the mass of the sun. The way they did it was they found the mass of the black hole by looking at the orbits of the stars very close. But then you have to go very, very close to the black hole, which means that they needed exquisite resolution. In the middle of our galaxy, this is a very nice picture from the Keck telescope, the largest telescope in the world, very high resolution, but you can't see the black hole, right? Black holes can't be seen. So that's where it should be, but there's a star cluster around the black hole. And so these people targeted the star cluster and tried to find the orbits of these. So the Keck telescope has two telescopes, 10 meters across in Hawaii. This is one of the systems used for this. And if you look at the Keck telescope, it is 36 mirrors, and each mirror can be independently moved. And the way they achieve this very high resolution is by a method called adaptive optics. What happens is that as the light comes to the atmosphere, it gets blurred because the images get blurred because the entire atmosphere has lots and lots of layers of different air of different pressure, temperature, and density, and the refractive index varies along its path. And as a result, the light that arrives at the camera moves around quite a bit. That's why stars twinkle. And if you take an image, it averages over a large angular size, and it blurs images. So what the telescopes like this do uses adaptive optics, which means that it actually in real time uses computers to change the shape of the mirror to compensate for that, taking the information from a secondary telescope that tells it what's happening. And so you can see that, for example, this is an example from the Keck telescope. The galactic center would normally look like this if the largest telescope in the world were looking at this. You can see all these stars. You can't see the black hole, but it's all a blur. But using this amazing adaptive optics technology, you can get such amazing resolution that you can start seeing individual stars in there. And the black hole is sitting right in that dark space in there. So you can take that. And this is what these two people, these two groups did. Andrea Ghez in UCLA, working with the Keck telescope, and Reinhard Genzel, working with the Max Planck Institute, working with the VLT, the 4 VLT telescopes, 8.5-meter telescopes in Chile. And this is in Hawaii, from the northern and southern hemisphere, both looking at the same place. Right from the 1990s, Genzel started first in the early 90s. Andrea Ghez started in 1995. And then they started monitoring and these are real pictures you can see this is probably a better one. You can see where you can see the pictures of the orbits of the stars. This is a real movie taken with the positions of the stars as taken from 1995 onwards. You can see it goes up to 2019. You can see this, it's lovely. It's one of the most wonderful movies that you will see. And these are stars very nearby. You can see that bar is 1/10 of an arc second, very, very close to the black hole. The black hole is where this white star is. You can't see it, but you can see all these stars have elliptical orbits around the central black hole. And if you take one of these, the earliest one that was used to get this result was S2, which has a 15.2-year orbit. And so from all these various nice elliptical orbits, they found some wonderful results. So S2's orbit, 15.2 years, you fit a relativistic Kepler's orbit to this Kepler's third law, and you find a very simple 4 times 10 to the 6, 4 million times the mass of the sun comes out to be the mass of the black hole, which is sitting there at the focus, one of the foci of this ellipse, just like Kepler's law tells you. So this is how, for example, they found the supermassive black hole, the mass of the supermassive black hole in the center of our galaxy. Now I'm going to talk about stellar mass black holes and how to detect them as we move on. So for example, we now know that there's only one supermassive black hole in the middle of our galaxy, or in each galaxy, but the galaxies have millions of stellar mass black holes, all many of them in the disk, but all over the galaxy. Now, how do you find them? One way to do that is to look for them in binary systems. More than half of the stars in our galaxy are in binary systems. So, for example, you can have two stars, one a more massive star than another one, which is a smaller one, maybe typically if in a binary star. So what happens is that the more massive stars evolve first. They go and they finish their fuel, and if it's a very massive star, more than about 4 times the mass of the sun, what will happen is that it's going to explode into a supernova and leave behind a very compact object. It could be a white dwarf neutron star, or in this case, say a black hole. So a black hole now exists going around a binary star, another star, which is a normal star, but it is smaller than the progenitor of this black hole. So eventually, this other star is also going to evolve and become very large. And as it becomes large, its outer layers will have less gravity pulling it, keeping it with the star. So this will start falling onto the black hole. The black hole will pull it out, and then the mass, as it falls in, it will have angular momentum, so it won't go straight into the black hole. It'll form a little disk around it. This is called the accretion disk. So this accretion disk is matter that exists around the black hole. It's not inside the event horizon of the black hole, it's outside, but it gets very, very hot because of the immense gravitational potential energy of the black hole. And it can get as hot as 10 to the power 7 degrees Kelvin. And when things get that hot, they emit X-rays. That's the idea. So this is an artist's picture, and it shows how this can emit X-rays. So this is, so once this emit X-rays, in the electromagnetic spectrum, this is the visible light in the middle, but the higher frequency, higher energy part of it is the X-rays, which has smaller wavelengths, and and that is what very hot things emit, ultraviolet and then X-rays. The problem with X-rays is that it's very hard to form images with X-rays because they, as you know, go right through you. It goes right through mirrors if they are incident at normal wavelength. And so the other problem with X-rays is that normal incidence, that is. The other problem with X-rays is that you cannot detect X-rays at the Earth because the atmosphere is opaque. Other than around the optical window and the radio window, the atmosphere is opaque. So so you have to actually take a satellite and put it an X-ray telescope and put it in space, and then you have to build special mirrors to focus these things. So here's an example: the Chandra X-ray Observatory, which is responsible for detecting almost all the black holes that have been found in binary systems in our galaxy and in neighboring galaxies, has this amazing orbit which goes out to 100,000 kilometers. Sorry, 100,000 kilometers, and has a 64-hour orbit. It has to go away from the radiation belts around the Earth, and it has got these special mirrors, which is like this. Which what happens is that in order to focus X-rays, you cannot actually have normal incidence. They have to be the X-rays have to come at very small angles from the surface, so it has to have grazing incidence. So as a result, these mirrors are very long, and slowly they make small deviations in the orbit, in the trajectory of the X-ray photons, and they focus them onto these detectors. And as a result, you will have you can see that the Chandra Observatory is very long. It's about 5 meters long, and X-rays come in and they get and focused on the mirror, on the cameras. We have the Indian observatory now called AstroSat, which actually has one of these X-ray telescopes, the soft X-ray telescope, which has similar mirrors, and I can show you. These are the AstroSat mirrors. These are the Chandra mirrors, and they are nested mirrors that can focus these telescopes. then Astrosat now, of course, has been doing a lot of these observations of black holes, black hole candidates and black holes and things like that. So I'll give you an example of how this works. Aniket and Sarita, I'm going to take 5 more minutes. Just let me wrap up because I'm going to talk about another thing. So here's an example of my own work on Centaurus A. Centaurus A is a nearby galaxy. This is an optical picture of Centaurus A, which is taken with a small telescope, optical telescope. This is optical region. So everything that you see in here is a few thousand degrees hot. The stars, like our sun, are a few thousand degrees hot. They emit light, optical light. But when the Chandra X-ray telescope, for example, looks at the same galaxy, it looks like this. And here, everything is 10 to the power 7 degrees hot at least. And here you see the supermassive black hole in the middle has lots of gas around it, is emitting a jet, relativistic jet, that this is about 1.5 million seconds worth of observation with the Chandra X-ray telescope. And you can see this emits, but all these point objects that you see, these are X-ray binaries in Centaurus A. I had a student who did his PhD thesis on all of these objects, modeling each of them. And many of them are binary systems which have neutron stars in them, but some of them are like this one, for example, like that one. These are all systems which have black holes in them. You can by modeling these ones, you can find the nature of the black holes and the mass of the black holes. So I told you about the 2 or 3 different kinds of black holes. The stellar mass black holes I talked about, supermassive black holes. But what about these intermediate black holes? These are very interesting. So in order to target them, we are going into a new era. And as you know, in India, we are coming into these amazing new facilities. India has now gone into the big league in astronomy in the world. And we are collaborating with other countries in order to build these telescopes that are almost international facilities, new things in India. The 30-meter telescope, which is planned to be in Hawaii, is a bigger version of the Keck telescope. It's going to be 30 meters. It's going to have 492 segments instead of 36 segments of the same kind of telescope. And you can see it's a collaboration between the US, Canada, Japan, China, and India. And in fact, Andrea Ghez, one of the Nobel laureates this year, is part of this whole thing from her institute, which is a partner in this with us in building this. Her interest is, of course, building a much bigger Keck. So you can do the same thing in the middle of other galaxies, not just our galaxy. The TMT is going to do many other things, of course. But the most important facility that has come up to detect these black holes now, it comes from the discovery of gravitational waves, which got the Nobel Prize 3 years ago. If you remember, a lot of Indians were involved in this as well. And that comes from Einstein's prediction that not just this space-time is going to be curved around massive objects, but as things move in space-time, it will create ripples in space-time, which will go out in the form of waves, gravitational waves. So if you take the most extreme things like 2 black holes, and they're coming together, now it's not a normal star and a black hole like I showed in the X-ray case, but 2 black holes. They're going around each other, and they will rapidly decay and merge into 1 black hole. And this will create quite a lot of upheaval in space-time. And this is being now being detected by the LIGO observatories, the 2 LIGO observatories that are currently there, Hanford and Livingston, 3,000 kilometers apart, detected, as you know, in 2015, the first detection of gravitational waves. Now we have about 65 or so of these detections till now, and each of them yields 2 black holes going in and merging and forming a 3rd black hole. So we detect 3 black holes in each of these mergers. And so the most massive one we announced a few months ago is a merger of something about 80 times the mass of the sun, together with something like 60 times the mass of the sun, becoming something like about 140 times the mass of the sun. It's the most massive thing we know so far in black holes. And this number, as you see, is going up with different objects we can see these two going up. And this is the whole zoo of black holes that have been found. If you look at the numbers here, these numbers are so many times the mass of the sun that are being found. And you can see the ones that are 5 to 10 times the mass of the sun, the purple ones are found through X-rays, like in the Chandra, and now with AstroSat, we are finding these ones. But with the gravitational waves, we are finding these ones, the blue ones, and they are very, very massive. So the stellar mass black hole zoo is growing, and it's very, very interesting times now to be a black hole astronomer. We're going to build one in India, LIGO, as you know. The third LIGO will be built in India. We are hoping to start building it this year, right in the middle of Maharashtra, near Hingoli. And so by the time it is built, 2027, 28 maybe, we will have a facility that is comparable or maybe even better than the ones in the US. And we will do this kind of international class science in India. I'll stop there with just a few books, my favorite books in the subject for you to look up. Anyway, back to you, Sarita and Aniket. My job is finished.
Uh, thank you so much. So while listening to that fantastic talk, I had a couple of queries. So typically in many popular books, when authors give a brief idea to general public, they say nothing comes out of black hole. You used a more precise term, which that no information comes out of black hole. So you want to elaborate on that choice of word?
Right. So it's like, for example, you can say nothing can travel faster than the speed of light. But what you really mean is no information can travel faster than the speed of light, which means that, and this is why, um, you can think about information in the sense, the Earth is going around the sun. If the sun ceases to exist, then the Earth will go around the sun for 8 minutes till that information reaches the Earth that the sun is not there anymore, right? And that information has traveled with the speed of light. And then the Earth will feel, oh my goodness, there is nothing there to go around. But those 8 minutes is when the information has not reached the Earth. It's information in that sense. So you can think of a black hole and you have an event horizon around it. And so no information can travel faster than the speed of light. So since the escape velocity of this particular region of space is more than the speed of light, then no information can come out. So you can't know anything about the matter that's inside. You cannot, for example, measure the nature of the particles. You can only measure from the outside the net result of what the microstructure is in there of the black hole, like the mass, for example, or the angular momentum, or the magnetic field, and things like that. So other than that, any more information is trapped within the black hole.
So some of our viewers want to know that you flashed this equation for Schwarzschild radius. So how this equation comes about?
Right. So I wish I had the full derivation ready here, but this is something that, of course, we teach in class. What Schwarzschild did was Schwarzschild solved Einstein's equation is an equation, right? So you need solutions, and you need solutions in various spaces, in various cases. So if you take a spherically symmetric case, for example, and think about a map that is a sphere sitting somewhere, and you look at what the metric would look like. The metric meaning the nature of space, the way you measure space around that black hole. Um, uh, the Schwarzschild came up with what we call the Schwarzschild metric, which kind of measures the very near a mass m, the, this nature of space, of the curvature of space, how you measure distances near the massive object. And there, the Schwarzschild metric has a term in it. So you saw that the term, it was gm over c squared, 2gm over c squared, and has a term in it which is 1 minus 2gm over c squared, which is a term that changes character as you go from the event horizon, outside the event horizon to inside the event horizon. So what happens is that, very interestingly, if you look at space and time, very, very interesting. If you look at space and time, uh, Einstein said that space-time are essentially part of a four-dimensional system. There are three dimensions of space and one dimension of time, and they are similar. They can be thought of as coordinates that are connected. Now, there's a big difference between them. In space, you can go in both directions. In time, you can go in only one direction, right? You can't go in the other direction. And if you look at how space and time behaves outside and inside this Schwarzschild radius, it is very interesting that outside, space is space-like, which means you can go in both directions, and time you can only go in one direction. But if you go inside the Schwarzschild radius, the nature of the Schwarzschild metric is such that time becomes space-like and space becomes time-like. So space is such that you can go in only one direction. That's why you can't come out of a black hole, right? So that's the interesting thing. And so the nature of space and time gets
So
swapped.
something which you mentioned very briefly in your answer, I just want to highlight it for benefit of viewers. So you said that Schwarzschild came up with a solution for Einstein's equation in a special case, and I think we should again highlight the fact that this is the simplest possible case for which we can think of, and then there have been other solutions for a more generalized cases. So Schwarzschild solution is not the only solution describing black holes.
Right. So for example, the curve solution, which is that of where the black hole is rotating, it's slightly different because then you have to bring in rotation. This is the most simple case. And then you can have various other asymmetries in the system and things like that. So this is simple case.
So I will just ask one more question before I hand over to Sarita. So in towards the end, you mentioned the various mega projects, including LIGO, and some viewers may wonder that gravitational wave discoveries have already happened for last few years, and there are two gravitational wave observatories already in place in US. Why do we need the third observatory?
Very, very interesting question, Aniket. I mean, of course, this is not just this is a 3,000 crore question, rupee question. Why do we need a LIGO India? There are many reasons we need it. You know, the LIGO observatories, the gravitational wave observatories are like microphones. They can detect things, but they cannot tell you where the sound is coming from or the gravitational wave is coming from. There's no directionality there. The reason we roughly know where these gravitational waves that we've detected coming from is that there are two in the US, 3,000 kilometers apart. So just from the timing of the arrival of the gravitational waves, you can figure out where. So the first one that was discovered, for example, had a 7 millisecond gap between the arrival times of two. So we know that, for example, there is a whole bunch of the sky from which it can get. But that doesn't narrow it down so that we can follow up and figure out what happened that caused that the gravitational wave. Um, in order to actually do that in a precision, you need a third observatory to triangulate. And then, for example, now the uncertainty, typical uncertainty of a source of a gravitational wave is, is maybe 100 square degrees or many more than 100 square degrees. Remember, the moon is 1/4 of a square degree. So but now with LIGO India, which is not 3,000 kilometers, but 30,000 kilometers apart, and having that triangulation, you can narrow down that whole thing to about maybe 5 square degrees. And if we do that, then you can have all kinds of radio telescopes, X-ray telescopes, optical telescopes following up that region to figure out where this happened, because invariably the event that caused the LIGO event will have lots of other interesting things going on that will help us learn about various interesting physics. So that's one. The second thing is that, you know, LIGO is limited by noise because it is detecting very tiny vibrations, and it has to eliminate a lot of local noise that cause much bigger vibrations. And one of the major vibrations is the vibration of the earth, seismic noise. Now, America is a horrible place for seismic noise. And it turns out the most stable place in the world for seismic noise is the Deccan Plateau. We have measured the noise characteristics of the site that we have chosen. It's at the frequencies of LIGO than anywhere in the US. So in principle, if we can make the instruments as sensitive as them, we can have a much better instrument in India, just because of a geographical location. So that's another reason. And of course, what is happening is that we are not doing gravitational wave detection anymore. We are entering into gravitational wave astronomy. So it's like Galileo used the telescope first and found a few things, observed the moon, observed the phases of Venus and things like that. That phase has happened now. Now, to do astronomy with gravitational waves, we need to build up the numbers. We know only about 60 such events right now. We need millions of events. And to do that, of course, by the time the Indian observatory comes, we'll start finding new kinds of objects, not just merging black holes, but other things, maybe gravitational waves and supernovae, gravitational waves from various other exotic objects. A lot of things to learn.
Okay, thanks. I can see there are lots of questions on YouTube, and we will take those. Sarita, you want to take some
Please
few
go ahead. Yeah.
questions?
Yeah. So I think one of the questions that we can take up, which is both from Zoom and YouTube, is about the black holes at the center of galaxies. So one of the questions from Zoom is from Arnav Birari asking whether all the galaxies have black holes at their centers, and another related one is from Gaurav Chaurasia, who's asking how are these black holes at the center of the galaxies created?
Very, very interesting question. Yes. So now the way we know from looking at, there are many ways. I mean, I just talked about two or three ways of detecting black holes. There are many other ways of finding and measuring black holes. And from what we know is that in the middle of all galaxies, there is a compact object, a massive object, but they're not black holes in all galaxies. Above a certain mass, which is roughly around about a tenth of the mass of the Milky Way, all galaxies have a supermassive black hole in the middle. It's absolutely true. We haven't found a single big galaxy that does not have a supermassive black hole in the middle. But if you look at galaxies that are smaller than that, which are called dwarf galaxies, galaxies that are satellite galaxies going around bigger galaxies, like our galaxy, for example, has 35 to 40, we know of satellite galaxies that are going around like moons around our galaxy. These are dwarf galaxies. And dwarf galaxies that are maybe a tenth or a hundredth of the size or even smaller than the giant galaxies, they do not seem to have black holes in the middle. Even our Magellanic Clouds don't have black holes in the middle, right? So not all, only the giant galaxies do, but there are enough giant galaxies in the universe, there are 10 to the 11 of them, that they have supermassive black holes in the middle. How they are formed is a very interesting question, and this is too early for us to give an answer to that. Um, Very interesting, of course, because I told you about stars exploding to form black holes, to leave behind black holes. The most massive star in our galaxy that we know is about 100 times the mass of the sun. So it can create a black hole that's smaller than mass than that. You can't create something that's a million times the mass of the sun. Now, if you saw that 140 times the mass of the sun black hole, you would even think where it came from. But we have seen it form from an 80 and a 60, right? So we know that black holes merge to form higher black holes. But can you have a sequence of mergers of smaller black holes forming a million or a billion times the mass of the sun? That has not been decided yet. A lot of people are very skeptical that the universe being 10 to the 10 years old, has there been enough time for stellar mass black holes merging to form supermassive black holes? So this is an unanswered question. There are some people who think that maybe in the early universe, when the universe was very small, the black holes that were formed were very massive. And so these are left over from a population of stars or population of black holes that were formed very early on, and things like that. So it will take a long time for this question to be sorted, and maybe you can be one of the people who can sort this. I mean, I'm very interested in the research that's going on in the formation of supermassive black holes.
Okay, so I'll ask you the next question, some related questions regarding accretion disks. So Devrath wants to know how large are accretion disks usually, and does the black hole not consume them quickly? Then Arnav asks, is the matter circling a black hole in an accretion disk orbiting the black hole at unfathomable speeds? And from YouTube, we have Kiran Mehta who wants to know why do they have accretion disks and why does it not happen in a sphere? Why is it not spherical around it? Why should there be a
Right.
disk?
So that's all very, very interesting questions. First of all, the accretion disk forms, as I said, because the angular momentum is difficult to get rid of angular momentum. Angular momentum is conserved. So as things are falling in, it's falling in from a neighboring star that is also spinning. And so there's angular momentum in the system. And so it can't go straight in. I mean, this is one of the reasons why the Earth is not falling into the sun, even though the sun is pulling it, because we have angular momentum. And so we are going around. And so similarly, as the stuff comes in. Now, there is a very interesting concept that, again, as students of astrophysics, one of the first things they read about, and that's called the Eddington limit. And that's what happens is as stuff that falls into a compact object, as matter falls in, there's a maximum limit up to which a black hole can accept matter, eat matter. And that is because as the black hole is accepting matter as it's falling into it, uh, it is also radiating. It's because there's some gravitational potential energy that's released, and so radiation comes out. And so the radiation that comes out has a pressure, and it will prevent other things from falling in. So soon an equilibrium will be reached between the radiation that's coming out as a result of the matter that's falling into the black hole, because it gets hotter and hotter, and it eventually falls in. And and the matter that's trying to fall in, and that equilibrium will limit the amount a black hole can eat per minute, say. And so that this is the Eddington limit. And so this regulates the amount that a black hole can eat. Otherwise, the black holes would grow very fast by eating matter, and it cannot, right? And that is another reason why you see these jets coming out of the neighborhood of black holes, because sometimes the amount of matter that's falling in gets too much, and they get ejected in the form of jets. The Centaurus A picture I showed you, for example, is an example of that. So the accretion disk then can last for 10 to the power 7, 10 to the 8 years, even up to 10 to the 9 years, because it depends on how long the matter is matter's falling. And of course, eventually, the star, the companion star that's supplying the matter is going to exhaust itself. And so the accretion disk will stay on till the matter is coming in, and there's a regulating force on the other side trying to stop that matter from falling in. And eventually the accretion disk will go away because A, the source has been cut off, and B, all the matter that was there in the accretion disk has fallen in or has been ejected in the form of a jet. So there's very interesting counter processes going on. And so these accretion disks, and when the accretion disk is hanging out there around this compact object, it is going to get hotter and hotter, and then it is going to emit these very extreme ultraviolet or X-ray at these temperatures, and these kinds of radiation. Okay,
Okay,
what's
so
next?
yeah, there are lots of them. So the next question from Devika in Zoom is, how is the spin of a black hole measured? And can a rapidly spinning supermassive black hole produce gravitational waves?
Right, very good questions. The spin of a black hole, there are many ways of measuring it. A very interesting way of measuring it is through the gravitational waves. You saw that time series I showed you about the two black holes merging, and you had the gravitational wave form where the frequency went up as a function of time. The first one that I showed you, the first one that was found, that whole thing lasts about a quarter of a second, two black holes merging. There's a 25 solar mass and a 30 solar mass black hole merging together. So, but there, in the waveform itself, there's information about the spin of the black hole, because the kind of the models that we fit to that waveform has one of the parameters, the spin. And from that, for example, the spin of the black holes as well as the final black hole, there's some limit on the spin of the final black hole. It's not very well constrained, but you can measure the spin. That's one way of finding it. Other ways are just modeling it. So there are many people who do models of black holes, of black hole mergers, for example, or or just the observations of black holes in various ways. And spin comes in. There are very few parameters that describe a black hole, right? You cannot have microstructure of a black hole. Black hole is characterized by its size, its mass, its spin, its magnetic field, and things like that. So there are these parameters go into the model of the black hole that you're trying to then you're producing something out of. So these things go in, and then you fit the observations of whatever you're observing in the gravitational wave case, the waveform, for example, and that gives you the spin of the black hole. Now, as the black hole spins, whether it can emit black hole, it's actually the spin of the black hole is not like it's hard to think about it as spinning as a top, because the spin's happening. The spin kind of is a parameter that characterizes the angular momentum of the black hole, right? Now, a neutron star, for example, which actually is something you can see the surface of a neutron star. It's very rapidly spinning. It's a pulsar, for example. The fastest pulsar that we know of has a period of 1.5 milliseconds, right? And so it's spinning a few hundred times an hour, a second. And so what it does, and you can actually see it drags space-time around it. You can see the effect of it, and it's radiating gravitational waves. There was a Nobel Prize given to Hudson Taylor, who found a binary pulsar, two pulsars going around each other, two neutron stars going around each other, and they measured the way the system is slowing down and found it exactly matching the expected rate of gravitational waves that would be radiated by the spin and orbital angular momentum of these systems. So to some extent, you can think of black holes being an extreme case of the neutron star, except that you can't see the black hole spin because you can't see the surface of the black.
So there's a question from Varun asking whether you can elaborate on the photosphere just outside the event horizon. And this is not related, but I thought I'll put it across anyway, is from Dhruv asking whether it is true that black holes can be made on Earth itself in the laboratory. So they're two different questions.
So the
One is about the
photosphere,
horizon.
yeah, I mean, I would, instead of my trying to hand wave and explain to you, I would like you to go and read about the photosphere on the many, many articles that were written when the Event Horizon Telescope found a famous image, which looks like a medu vada or whatever, a donut, around the black hole in the middle of M87. And that, of course, will be the subject of a Nobel Prize coming up very soon, I think. But a lot of articles were written about the very famous image of the supermassive black hole. And there, what you see is essentially what is known as the photosphere, which means that it is the closest distance, which is not quite the event horizon for various reasons connected to the details of the various orbits things can have around a black hole. For example, if you have a material star, it can have the various orbits around a black hole, but there is a limit out to which it can have a stable orbit. Similarly, you can have photons that can be around a black hole, but you can see them only out to a certain distance, and things like that. And so that is the last bit of light that you can see around a black hole is what you saw in that picture. And so there are a lot of, for example, YouTube videos explaining what is the subtle difference between the event horizon, the Schwarzschild radius, the last stable orbit, for example, the last stable, the last photon kind of in a radial sense that you can see around the black hole and things like that. Go look at it, and there's a lot of nice articles there.
Yeah, the other question was
Oh, the
about
other
whether
question
one
was
can.
whether we can find. Um,
Yeah.
I um, I'd be very, very afraid if somebody creates a black hole in my laboratory, right? Because question is whether what you mean by a black hole there. There are a lot of people who, talk in analogies like they say, this is the God particle, or this is a whatever. I've seen the face of God. I've done a black hole. Now, what sometimes people mean when they deal with high energy experiments, you'll sometimes say that this experiment created the Big Bang in the laboratory, right? It just means that energies that are comparable to the Big Bang were 4 10 to the power minus 30 seconds created in the lab. It was not that. So you can probably take a characteristic of a black hole and say for a very transient period, we created densities that are almost the same as a black hole, something like that. Such things have been claimed. But I don't think if for example, somebody creates a black hole in the middle of this room, I don't see how this building can stand, right? So, so there are differences between a transient phase that is created, where you can claim, I mean, there are some of the higher elements in the periodic table are only created for a very short period of time, and then you can claim it's created. In that sense, you can probably create black hole densities in an experiment where, say, two beams of particles meet at a very high speed, and for a very transient period of time, you can have a very high energy or a very high density, that kind of stuff. Other than that, I can't think of a scenario in which you can create a black hole in the middle of a lab.
Sarita, there are several questions people are asking since we earlier said black holes won't emit anything. So they want to know how that reconciles with Hawking radiation. What exactly is Hawking radiation?
Okay.
So
So this
can
is
you,
a question that's asked all the time. Every time I give a black hole, there's a Hawking radiation question. So let me let me talk about that. So yes, black holes do not emit anything, but that's in the classical sense. In general theory of relativity tells you that. But there's something called quantum mechanics, and quantum mechanics is a probabilistic way of looking at things. And in detail, in quantum mechanics allows certain things that classical physics does not allow, right? And Hawking came up with this very, very smart idea. It was so smart and so wonderful that he published it in Scientific American instead of a regular scientific journal. And his idea was that, in uh, if you have in general, quantum mechanics tells you that there are particles annihilating into energy because E equals mc squared, and out of energy particles being created all the time. In vacuum, what happens is massive particles annihilate and then create particles. So a photon that has an energy that is much bigger than the rest mass energy, E equals mc squared, of two particles, and antiparticle and particle, then it can create these two particles, and then they can annihilate all the time. This is always happening. So in a classical sense, this is not there, but in a quantum sense, this is always happening at very short time scale. So Hawking came up with this very smart idea that, very near the event horizon, what if two photons split into a particle and an antiparticle, and one of them fell into the black hole? What will happen to the other particle? So from outside, you will see, oh, suddenly there was nothing there, and then one particle is left there, it's coming out. So theoretically, if there a particle which has energy, mass energy, is coming out of a black hole, that means, in the resultant sense, that the black hole has emitted something, right? Now, note this is a very rare case. And so this is a kind of a loophole in this whole kind of classical argument that nothing can come out of the black hole. Is this a realistic thing that you can detect? Nobody's detected this yet, but there are mechanisms of detecting it. But let me float a number here. For a stellar mass black hole to completely radiate the energy it has in terms of Hawking radiation, for something that has a mass of one solar mass, will take 10 to the power 60 years, 60. The universe is 10 to the power 10 years old. right? You can already see that in time scales that are of the age of the universe, a black hole can't evaporate much. It can give up a little bit of its mass in form of radiation. And you can imagine how faint that radiation would be for normal black holes. For supermassive black holes, maybe this can be detected, and people are designing experiments so that around supermassive black holes, Hawking radiation can be detected. There are some, but the wavelengths are very difficult to pin down. I've seen an experiment that has been designed in which maybe in the energetics will fall in the X-ray region for certain black holes, which will be very, very massive, maybe primordial black holes and things like that. So this is a very exotic science. This is doesn't make much of a difference to the black holes themselves in terms of them changing in matter, in its matter content. But you would find a lot of people are very interested in this because, first of all, Hawking is involved. And secondly, because this is a loophole, this is a way in which a black hole can emit something. But actually, for practical purposes, it's a very minor thing. It's only a very interesting theoretical exercise. Let's see
There's
who else.
an Yeah, lots still to go. There's an interesting question, I think, from Devika, who wants to know how whether in the galaxies in Milky Way, for example, we have a bulge. So is that related to the presence of the supermassive black hole, and how the supermassive black holes affect do they affect the shape of the galaxies?
Very good question. Very interesting question. So, there is something called the Megorian relation, which shows that there is a relation between the mass of the supermassive black hole and the size of the bulge of the galaxy. So, the galaxies are made up of a bulge and a disk, the spiral galaxies. The elliptical galaxies are essentially bulge only, no disk. So, and we now know there's a very nice relation with quite a bit of scatter, but there's a relation between the mass of the black hole and the size of the bulge of the galaxy. Now, in a spiral galaxy, you see the bulge is very small, only a small fraction of the mass of the galaxy. And that is why spiral galaxies have smaller black holes or lighter black holes. The black hole in the middle of our galaxy is 4 times 10 to the 6 times the mass of the sun. If you look at an elliptical galaxy that's equally massive to our galaxy, the black hole in the middle, because that's just bulge. So the black hole in the middle of that galaxy will be 10 to the power 8 or 10 to the power 9 times the mass of the sun. Okay? So that is telling us something. We don't know what it is telling us, but one of the major areas of research now in the evolution of galaxies is to find out this connection between the black hole. And it's telling us that the black hole is connected to the bulge and not the disk, because there's no correlation between the characteristics of the disk mass, and the black hole mass in galaxies. So there are theories that say that maybe black holes formed early on, black holes formed first, and the galaxies formed around them. The bulge of the galaxy formed first. The bulge apparently has the oldest stars in the galaxy. They are redder than the rest of the galaxy. They have the oldest stars. So maybe the galaxy formed around the black hole. But this is not a very popular theory, but this is a very important theory. Martin Rees's papers, for example, early on was on this. The more popular theory is that the black holes form within the galaxy after the galaxy is formed, but it forms at the center, and that's where the bulge is, right? It turns out that the most of the growth of the black hole, if it is growing by drawing in matter from its surroundings and stars falling in and things like that, would be from the bulge. So it is related to the bulge. So there are popular models of galaxy formation and galaxy evolution that try and co-evolve black holes and the bulges of galaxies. But this is a very interesting area of research. It hasn't been resolved yet, but such correlations have been found.
Okay, another question I think from YouTube. Muskan wants to know about, for example, the space-time fabric. How can we explain gravity with space-time fabric concept when all the planets and other bodies of our solar system don't revolve around the sun in the same plane?
That those two are not connected. The space-time fabric is if you remember the picture I showed you, it kind of it just tells you that space-time itself has a character. It's something. In Newton's idea of gravity, space-time is vacuum. There's nothing. There's no space, right? There's empty space between the sun and the earth. But in Einstein's way of looking at it, space-time itself is something, and we call it the fabric. It looks like things like cloth or something, but it's something. And what the mass is doing, the mass of the sun, the mass of the earth, is causing a distortion in its shape. So it is determining its geometry. I won't call it a distortion. I will call it the geometry of space-time. So locally around the sun, space-time is curved because there is quite a lot of matter there, and the Earth is going around because it is trapped in that curve of the sun. Now the other planets are also going around the sun in that general curve of space-time, and they're all trapped around the sun. The reason they are in a plane is more than this. This general curvature of space-time does not determine the fact that they're in a plane. That is different because if you think of the way, and that is telling us something, it's giving us a hint as to how the solar system formed. When the solar system formed, they formed from a large cloud of gas and dust. And it formed, as we know, it looks like most of the planets that we have looked at have the same age, and the moon has the same age as the sun almost, and stuff like that. So we think that they all formed at the same time, and the sun formed in the middle, and then were formed with a mass that could ignite a nuclear fusion in the middle. And then the other bits of the solar system condensed to form the gaseous planets and the terrestrial planets and things like that. But this entire nebula from which these things formed would have had an angular momentum, would have had a rotation. And as it collapsed, the rotation would have gotten faster and faster, as you know, because angular momentum is conserved. And when there is angular momentum in a system, there is an axis around which rotation happens. It determines an axis. And things tend to form disks, planar structures, perpendicular to that axis. This is the same reason why spiral galaxies are flat. They would have formed from large, slowly rotating clouds collapsing and the thing speeding up. But since there is a well-defined angular momentum axis, then the collapse happens perpendicular to that, or roughly perpendicular to that. And this is why most galaxies are disk-like systems. Similarly, there is quite a lot of analogy between spiral galaxy disks and planetary disks, the protoplanetary disks. You will see simulations show spiral structure in them and things like that, and they form these disks, and then the disks break up to form the planets and the asteroids and the various systems in there. So that's what's happening in the general vicinity of the sun, and the real structure of space-time doesn't come into this really. That doesn't determine what the shape of these orbits will be. The fact that they're all in a plane comes from the fact that the nebula that collapsed to form these planets were all connected at the very beginning.
Okay. So Arun wants to know how one gauges the age of a stellar mass black hole, and recent merger events which release gravitational waves can be detected and an estimate may be made. But what about black holes that we observe that are already there? How can you determine the age?
You can't. I don't think you can. There are, for example, neutron stars. You can find the age because you can find the way they're spinning down. So their rotational periods change, and then you can kind of extrapolate and try and figure out how old this neutron star is in terms of the spin. Black hole spins can't be detected so directly, and so if you find a black hole that's out there, it's hard to know where it came from and how old it is. And now that we know that black holes are often formed from mergers of other black holes, so it is hard to know whether this black hole has come from the merger of two others. So I can't think of a way of actually finding the math. I mean, doing an archaeology on a black hole and finding the age, really. I don't think you can, because black holes don't give you that kind of information. Black holes just tells you what mass it has and the general angular momentum and stuff like that. It would be very interesting if you can come up with something somebody who can find out a way of measuring the age of a black hole would become instantly famous, I think.
Okay, there are a few questions about what happens inside a black hole. For example, if a person enters, what would happen? And if you have two clocks which had same initial time matching, what happens to them once they enter? And I think there are a few more.
Well, don't go near a black hole. I had a slide in there, I think. Can you see my thing again?
Yes.
Let me see if I have. I had a slide in there that to show what happens if you fall inside a black hole, right? And this is what happens. So if a macroscopic object falls inside a black hole, comes very near a black hole, the black hole has immense gravitational force, and so the derivative of that is also very important because it has a tidal force. What is a tidal force? It means that, say, this is a person who's falling into a black hole, and it's going feet first. The black hole's um, gravitational pull on the foot and the head, these two differ quite a lot because it is, it is the gravitational force divided by 1 over r squared and divided by r squared. And that as you come closer and closer, the difference between the head and the foot it becomes immense. And if you go closer, it just pulls you into spaghetti. And that's why it's called spaghettification. So you become very, very thin and very long as you go inside a black hole. So that's something to avoid. But this happens only very near a black hole. I think that
So
was a
about this, I have a question.
yes.
So is this something which a distant observer will see, or is this something which will actually happen to the
Very
person falling?
interesting. So there, of course, time changes too, right? So the way clocks tick changes in terms of, so the clock that is on the astronaut that's falling in um, is changing in a different, is ticking in a different way than somebody who's looking at this person from a distance. And they're completely different. In fact, I told you the way the Schwarzschild metric works. And as you cross the event horizon, time becomes like space, etc. But as the person approaches the event horizon, the time is dilated so much of the person that in the person's frame, it will feel like this person has never reached a black hole. It takes infinite amount of time for the person. So the person is going to get spaghettified to a very long time. Whereas somebody who's looking at it from outside, maybe from the spaceship where the astronaut fell out, are looking at the astronaut and actually will see zoom go in very fast, right? So the times are very, very different. And so this also leads to very interesting science fiction concepts. I mean, of course, everybody's thinking of Interstellar and movies like that, where such things were talked about. So yes, so time ticks very differently, but things falling into a black hole. So you can think of not just people, but you can think of a material falling into the black hole. The same thing happens. And this is
So
also, I mean, yeah, related thing everybody asks in black hole talks is what happens. How can you time travel through black holes, etc. But right now, the technology is limited by the fact that this is what's going to happen to you if you try to go through a black hole into another part of space time. Yeah.
since you mentioned Interstellar,
Mm.
I want to just bring up that movie. So two things I want you to comment on. One is that those massive tides on the planet in that interstellar movie, and the second thing, the way that big black hole was illuminated. So why that particular way the light around black hole appears?
Why don't you talk about it? You know about it, Aniket. You tell us.
No, you are the speaker. So
You tell us. Well, a lot of the simulation that was done about the way the space-time behaves around that black hole was
yeah,
done through numerical simulations.
I
So
remember this was the first time this kind of simulation was done. But before interstellar, actually these kind of massive simulations were never done.
absolutely, and Kip Thorne was involved, right? Kip Thorne, who got the Nobel Prize for the gravitational waves, his group was involved in doing those simulations, and those are state-of-the-art simulations. There are scientific papers written on those simulations, published in Physical Review. So not many movies do that. So they're very realistic, but they lead to all these very counterintuitive effects. Like, for example, how as you approach the black hole, you can see the back of the black hole come to the front, right? Those things come out of the simulations. And unless you see those simulations, it's hard to even know that those things happen. And these are state-of-the-art numerical solutions of Einstein's equations that are being done now.
Yeah,
So
we should only warn our viewers that if they read the corresponding paper, the results from simulations were slightly less dazzling than the ones which you saw in the movie. So they, they actually spiced up those results a bit to make it more attractive in the movie.
that's right. So
Also, I think,
yeah.
sorry, just to, since this topic came up, because there were simulations involved, I think a lot of viewers also are wondering because the later part they actually show lots of things happening inside the black holes. So they want to know, are those realistic too? Because these simulations, huh? So,
See,
so can
that's
you
the interesting
comment on
because
that?
when you
Yeah.
when you put down, I mean, I've seen there are YouTube interviews of Kip Thorne. If you track them down, you'll see him discussing these things as well. Kip Thorne was involved, and his students were involved in some simulations. But the movie finally did not use all of the simulations and kept to the science. The dazzling picture of the warped accretion disk, etc., and how you and how the time and space were seen around the black hole was very well done, I think, and that was accurate. But certainly, then the movie took liberties with the simulation, and there is no simulation, no physics, nothing that you can do when you go inside a black hole because we don't know anything about what's inside the event horizon. So though that is speculation, that's where fiction comes in, and that is why that was not a documentary. I mean, Interstellar was not a documentary; it is a work of fiction, and so the author can take that license and try and imagine what's inside. That's
Yeah,
fun.
correct. That's right. But if people who are not very familiar may not know where the simulations stop and where the creative liberties begin. That's why I have brought this up. Yeah, Niket,
Yeah,
go ahead.
I should tell you that when that movie came out, I
Mm,
was not completely convinced that these kind of extreme tides would happen on a planet, even if it is very close to black hole. That
mm.
at one instant it is just less than 2 feet of water under you, and the next instant there is a tsunami. So for that year we had a question for in the Indian Astronomy Olympiad for the students to actually work out what will be the tide heights for a given set of black hole parameters, and it turns out that part of the movie actually is quite true to reality.
Yeah.
But time scales? What about time
Yeah, but,
scales?
same time, similar time scales.
Oh, I see. Okay.
You can tune in the black hole parameters to get that effect.
That's actually quite a fun exercise, even at the Olympiad level, that you can go and look at these time scales. And of course, Olympiad questions rely on school level physics that people learn. That was a very smart question, I think. And also, it shows that simulations often point out very interesting effects that you hadn't thought of before, but then you can go back and use your normal knowledge of physics to then figure out why that happens. That was a very striking effect, no doubt. But yeah, I mean, there were other effects in the movie that were not really very realistic.
Sarita, we can take, I think, a couple of more questions, then we should close.
Yeah. So I'll have a look at Zoom. Can you also look at the YouTube if possible and select some? From here, one thing that I can think of is about gravitational lensing. So Purvi wants to ask, is there a way to observe black holes or phenomenon around it through gravitational lensing?
Yeah. So certainly, I mean, I didn't talk about gravitational lensing at all today. And one of the consequences of general relativity, just like gravitational waves is a consequence of general relativity, this whole thing about light light always follows space-time and goes from point A to point B, following the geometry of space-time. And as a result, it bends around massive objects, and that creates the lensing effect. Now, near black holes, the space-time geometry is pretty bent, and so black holes should cause quite a bit of distortion in light rays. So there are some very interesting phenomena that are being discovered around black holes. One is called microlensing, for example. So for example, stellar mass black holes in our galaxy or in neighboring galaxies are moving around and you don't see them if they are single black holes. I talked about binary black holes, causing X-rays or whatever. So now there are some claims, for example, that if you stare at a stellar field for a long time, this has been done by choosing a stellar field, for example, in the Large Magellanic Clouds, which is beyond our galaxy. And there are telescopes that look at this, and suddenly you see that one of these stars, their brightness goes up and then it comes down again within a few days. And this is often interpreted as maybe a black hole in our own galaxy passing along the line of sight. And as it does, the light that comes around that black hole gets focused and causes a blip. Now, there are ways of distinguishing this phenomenon, which is microlensing, from the star itself going blip and coming down. And the way to do it is, for example, gravitational lensing itself is achromatic, which means that it doesn't depend on the color of the filter in which you're observing this image. So it should be exactly the same amount in the red and in the blue. Whereas a star that itself, for example, is brightening because it's gone nova or something like that, has a color dependence. So there are ways of testing this. And there are claims now that such microlensing events have been found in which might be caused by stellar mass black holes. So that's one. There are many other things that you can think of in which such black holes can be detected. For example, galaxy lensing is a very interesting subject now. That is lensing of distant sources due to single galaxies. And you can find out the distribution of matter within a galaxy by looking at the lensing effects of on distant sources. Or maybe the supermassive black hole in the middle of a galaxy can make a difference. Such resolution has not been achieved yet, but one can think of such things happen. So yes, so in general, in principle, the gravitational lensing due to black hole can be detectable, and it's probably been detected in microlensing.
Okay, we'll take one final question from YouTube. This is by Kedar Soni, who wants to know, can the Higgs field penetrate through the event horizon? And if not, then does this information of the gravitational field of the interior reach the exterior?
I have no idea. I do not know the answer to this question. There are many people here who might know the answer to this question. Does Harvinder know? Does Jasjit know? I saw Kinjalk was there. I do not know the answer to this question. I'd be happy to find out from
Harvinder, are you around?
Jasjit. Jasjit is also around.
I think Kinjalk is probably the best person to answer this
yeah,
question.
Kinjalk should know, but he was there. He's gone now. I think he's
can the Higgs field? That is the question.
I have no idea. That's a very
penetrate.
interesting. Well, it's a variant on the Hawking radiation question.
Yeah, I think it's the answer you have already given. I think that is the answer. So
Yeah, it's very similar way in a quantum quantum way. I suppose you can
yes.
do it, but just like the Hawking radiation. But I can't. I've never seen this done, so I don't know.
Okay,
Anybody else?
so yeah,
Yep, I think it is 18:25, so we will have to move towards
wind,
close. Yeah,
yeah, wind up.
Harvinder, would you like to?
So, thanks a lot, Shomak, for giving us an exciting talk on a fascinating subject and taking us from right from the conjecture of John Mitchell by about dark stars to currently what are the mega projects that are in place and coming up, and also a large number of research problems that people can explore and work on. Thanks a lot, Shomak, and we will meet on April 11th next for Ask an Astronomer series of talks. Thanks a lot, everyone.
Thank you very much. Thanks very much. Thanks everybody for coming.